This year, we have somebody who's a stargazer, a mediator of stars. There's a lovely pre-Socratic story about a pre-Socratic philosopher who was so busy watching the stars that he fell into a pond and died. We have always been intrigued by what lies beyond. And to take us through that, to make us understand what is the connection between the astral world and we who walk on Earth, there is Ganesan Srinivasan, who not only is a very, very prominent astrophysicist, but is also trying to popularize science in India. He's producing a series of books about the stars. It's called The Revolution in Astronomy, and it's geared for children as well. And he has a wonderfully intriguing title which says, Can the Stars Find Peace? Please welcome Ganesan Srinivasan.
Given this extraordinary nature of this meeting, and perhaps a slightly peripheral nature of my talk, perhaps I should begin by quoting from Henry IV. First my fear, then my courtesy, and last my speech. My fear is your displeasure, my courtesy my duty, and my speech to beg your pardon. Was there a beginning to the universe? Was there a beginning to space and time? Will there be an end? Although these questions lie at the base of all religions and all philosophies, till very recently, these questions remained outside the premise of science. Today, they have acquired meaning, and we are witnessing a truly great revolution in science, not just in astronomy. Our story begins about 100 years ago when Einstein published his famous general theory of relativity. Although mathematically this theory is very complicated, the physical content of this theory can be stated very simply, as Einstein himself did. There is nothing in the world except empty, curved space. Matter, charge, electromagnetism, and all other phenomena are only manifestations of the bending of space. So Einstein said, physics is nothing but geometry. 2 years after he published his theory, Einstein turned to a study of the universe as a whole. He believed that the universe must be static. There was no evidence otherwise. But he had a problem. Since every part of the universe will be attracting every other part of the universe due to mutual gravity, the universe should obviously contract like a stone falling to the ground. So if the universe had to be static, then something must be holding it up. So he artificially introduced a cosmic repulsion to make the universe static. In 1917, we knew very little about our universe, but this was to change very soon. Through a series of spectacular discoveries made in the 1920s, the American astronomer Edwin Hubble gave us new insight into the true size and nature of our universe. In 1923, he emphatically established that our galaxy, the Milky Way, is not synonymous with the universe, and indeed there are other galaxies or island universes. Today we know that there are more than 350 billion galaxies such as our own, each containing a million stars. Now, are these galaxies the building blocks of the universe in the sense that atoms and molecules are the building blocks of air in this room? Hubble showed, through another discovery, that even these giant objects containing million stars are not the building blocks of the universe, but the building blocks of the universe are large clusters of galaxies containing many thousands of galaxies bound together by mutual gravity. We know that there are more than 25 billion such clusters of galaxies, and these are the building blocks of the universe. And then in 1929, he made the sensational announcement which shocked everybody. He announced that no matter which cluster of galaxy you looked in the sky, they're all moving away from us with enormous speeds. And the faster they are, the faster they are receding. The farther they are, the faster they are receding. And as he remarked, the clusters of galaxies are running away from Earth as though there was plague on Earth. Now, it turns out that 2 years before Hubble actually published his discovery, a Catholic priest in Belgium by name Georges Lemaître suggested that this recession of galaxies that Hubble had discovered in the fairly nearby universe perhaps might represent the expansion of the whole universe. So as the universe expands, all distance scales will expand, and therefore the distance between galaxies may expand, and this would explain the phenomena that Hubble had discovered. Now, at this stage, we run into a problem. What do you mean by the universe expanding? What is it expanding into? Because by definition, the universe is everything there is. Now, that's one of the difficulties with the way our brain has evolved. We live in a world of 3 dimensions. It's very difficult to imagine how the universe could be expanding. So what we have to do is to pretend for a while that our universe is actually 2-dimensional. And then I can visualize, standing in the 3rd dimension, what an expansion of a 2-dimensional universe could possibly be. Now, according to Einstein's theory of relativity, the geometry of our universe, the geometry of space, were we to imagine it to be 2-dimensional, can be one of these 3 possibilities. The universe could be, space could be curved like a football, or flat as this floor, or curved like the saddle of a horse. And the general theory of relativity of Einstein tells you under what conditions the geometry of the universe will be one of these 3 possibilities. Now, in the 1940s, the great physicist George Gamow wrote a popular book called The Creation of the Universe, in which he drew this cartoon. He said, let's imagine the universe to be 2-dimensional for the purpose of our discussion. And let's take a balloon, and the surface of the balloon is our universe, and let's plot galaxies on this balloon. And as the balloon inflates, you will see that the distance between any 2 galaxies will increase. And this is exactly what Hubble had discovered. Now, after Hubble discovered his phenomena, and Georges Lemaître said that this might in fact represent the expansion of the universe as a whole, Einstein realized that he had made a blunder in artificially modifying his theory and forced the universe to be static. And he remarked, this is the greatest blunder of his life. Now, I would like to argue that perhaps he did not make a blunder after all. Now, a couple of years later, our Belgian Catholic priest, Georges Lemaître, proposed what became known as the Big Bang theory of the universe. He called it the hypothesis of the primeval atom. And what Georges Lemaître said was, the universe is expanding today. If you run that movie backwards, in the past, the universe would have been smaller and smaller and smaller and smaller. And in the sufficiently distant past, the universe would have been only as big as an atom. And he called it the primeval atom. Now, this primeval atom would have obviously been incredibly hot. And now, using the general theory of relativity of Einstein, it is very easy to estimate that when the universe was about 1 second old, the temperature of matter and radiation that would have filled the primeval atom would have been a million degrees, 1 followed by 12 zeros. So a veritable fireball. Now, if I take a cycle pump and I compress the piston, the gas gets hot. Conversely, if a container which has gas in it expands, the gas will cool. This is a familiar phenomenon. But the point to appreciate is that the same thing obtains for radiation. If there is radiation in a cavity, and that cavity is our universe, as the universe expands, the radiation will cool, just as matter will cool. And it occurred to a brilliant young physicist by name George Gamow in 1948 to suggest that perhaps our present universe must still contain the relic of this primordial fireball, but it would have cooled from a temperature of a million degrees to a temperature of about minus 270 degrees Celsius, or about 3 degrees Kelvin. Some 20 years later, 2 astronomers working in a telephone company in America Penzias and Wilson, discovered this primordial radiation which still fills our universe. It is there no matter where you look in the universe. And as George Gamow had predicted, its temperature was minus 270 degrees Celsius. But still, there was a great deal of skepticism about whether this discovery really proves that our universe began as an atom, as a point. But these doubts were laid to rest in 1965 by a profound discovery made by Roger Penrose and Stephen Hawking. They proved in a mathematically exact manner that our universe could have begun as a point or end as a point, or both began as a point and will end as a point. They didn't say this is what our universe did, but they said this is a rigorous mathematical possibility given the premise of Einstein's theory of relativity. And so, for the first time in the history of science, one could rigorously ask this question, which we have all asked since the time we were that old: was there a beginning? A great scientific revolution had begun. People suddenly remembered the extraordinary prediction of George Gamow in 1948, and people were convinced that the radiation that Penzias and Wilson discovered that fills the universe today, whose temperature is 3 degrees Kelvin, is in fact the relic of the primeval fireball. And a few years later, they were awarded the Nobel Prize for Physics for this extraordinary discovery. Now let's return to our story of our expanding universe. Now that we know that our universe is expanding, we can ask 3 questions. How fast is it expanding? What is the age of our universe? And what will be its ultimate fate? Well, you will appreciate that the expansion rate of our universe will really depend upon time, because the various parts of the universe are pulling each other, and therefore you would expect the expansion to slow down, very much as a stone thrown up slows down because the gravity of the earth is pulling the stone. So even as the universe is expanding, it must slow down, because the gravity of every part of the universe on other parts of the universe is forcing it to slow down. So what is the rate at which the universe is expanding today as we speak? Well, if you looked at a cluster of galaxies, which is at a distance of 1 million light years from us, it's moving away with a velocity of 25 kilometers every second. Another cluster of galaxy, which is twice far away, is moving at 50 kilometers per second. And one which is 3 times as far away is moving away at 75 kilometers per second. And although 1 million light years is an awfully big distance, 1 million light years is 1 followed by 19 zeros kilometers. Even though this is an incomprehensible number, please remember 1 million light years is just our backyard as far as the size of the universe is concerned. We now know that our expanding universe began 13 billion years ago. Well, I shouldn't really say that, because all we know is 13 billion years ago, there was a big bang, and the expansion of the universe began. Now, did the universe exist before 13 billion years, before the Big Bang? We simply do not know. Now, what will be the ultimate fate of the universe? Will it stop expanding and contract? Or will it go on expanding forever and become truly infinite? Well, let's look again at the analogy of a stone being thrown up. Now, if a stone is thrown up on the surface of the earth, if its speed is less than a critical value, which is 11 kilometers per second for the earth, then the stone will go up, slow down, turn around, and fall back. But on the other hand, if I throw it at 12 or 13 kilometers per second speed, it will eventually escape to infinity, and this is the notion of the escape velocity. In the same way, since different parts of the universe are attracting each other, you can ask, will the universe fall back on itself, or will it expand forever? Now, Einstein's theory says both are possible. The universe can either expand forever, which is the upper panel of this figure, or the universe will slowly slow down and eventually contract and end in a big crunch. It began with a big bang and will end in a big crunch. So the question is, which of these 2 possibilities obtains for our universe, the universe we live in? Now, that question can only be decided by answering the following question. Is there enough matter in the universe to pull it back? If so, will it contract in some distant future? just as a stone being thrown up is eventually falling back on the earth, or just as a stone can escape under certain circumstances to infinity, will the universe expand till it becomes infinitely large? Now, Einstein's theory of relativity answers this question in a very precise manner. Just as an engineer will say 11 kilometers per second is the speed, minimum speed at which you have to throw a stone so that it can escape to infinity. Now, Einstein's theory tells us that the present expansion of our universe will eventually slow down, leading to a contraction of the universe, if and only if the matter density in the universe is greater than a certain critical value. Like 11 kilometers per second, there is a certain density that Einstein's theory stipulates. And what is this magical value of density? It's a very modest amount, equivalent to the mass of 5 hydrogen atoms in a cubic meter. Now, you may not know what a hydrogen atom weighs. It weighs 1 divided by 1 followed by 26 zeros kilograms. It's an awfully small number, incomprehensibly small number. So Einstein's theory says, only if the density of matter in the universe is greater than this value, will our universe contract. Now you'd say, of course it will contract. Look, each one of us weighs 50, 60 kilograms, and we are not 1 cubic meter. 1 cubic meter of earth weighs many hundreds of kilograms. What are you talking about? You're talking about 1 divided by 1 followed by 26 zeros. So, of course, the universe must contract. But not so fast. Because although our density is about 1 gram per cubic centimeter, the density of water, which is why we float in water, the density of the atomic nuclei with which we are made of is 100 million grams per cubic centimeter. We are made up of matter which is 100 million grams per cubic centimeter. But because these nuclei of atoms are placed so far apart, our average density is only 1 gram per cubic centimeter. In the same way, you have to ask, although the matter we see around us, surely 1 cubic meter will weigh many hundreds of kilograms. All you want is 1 divided by 1 followed by 26 zeros. You have to ask, what is the average density of the universe? Because please remember, the distance between clusters of galaxies, which are the atoms of our universe, if you like, is hundreds of millions of light years away. And 1 million light years is 10 million kilometers. So, if you took a box which is 1 million kilometers in size in all 3 dimensions, if you could weigh all the matter in this box and divide mass by volume, you will get the answer to the question Einstein posed you, which is, what is the average density of our universe? Well, astronomers worked for 50 years on this question, and a few years ago they found a very good answer to this. That is, the average density of matter in our universe is only about equivalent of 1 hydrogen atom per cubic meter. Now, this should be compared with 5 hydrogen atoms per cubic meter that Einstein says there must be in order for the universe to collapse once again. So let me remind you once again that only if the matter density is more than this critical value will our universe eventually slow down and fall back on itself. Since the measured matter density of a universe is only about 1/5 of it, we have to conclude. I had 25 minutes and... Okay, fine. Therefore, the universe will expand forever. So, a few years ago, just about 5 or 6 years ago, physicists and astronomers concluded that our universe will not fall back on itself. Our universe will expand forever and ever. Now, there is a double trouble here. Not only there isn't enough matter in the universe for it to fall back on itself, it turns out that 85% of the matter that is present in our universe is not of the nature that we are familiar with. What is the stuff we are made of? We are all made up of atoms and molecules. Atoms consist of tiny nuclei consisting of protons and neutrons around which electrons are going around. And this is the matter that we are familiar with. What about the celestial zoo? That is our universe. We are talking of galaxies which come in all sorts of shapes and sizes. But the important thing to appreciate is each of these 250 billions of galaxies contain million stars. When we look up at the night sky, it appears to us that the region between the stars is empty, but this is not so. The vast space between the stars, there are countless gaseous nebulae such as these. Today we can say with supreme confidence that the Earth, the planets, the stars, the nebulae, you and I, in fact everything we can see in the universe through the radiation, not just you and me, but even Superman with his X-ray vision, that everything that emits radiation is made up of neutrons, protons, and electrons. And therefore, the great mystery is, what is this other 85% of the matter that pervades the universe? Well, we simply don't know, so physicists have called this the mysterious dark matter. So what I would like you to appreciate is that we simply don't know the 85% of the matter in the universe. It's a different matter that even that is not enough to make the universe contract. What we know is that this matter is not luminous. Even Superman with his X-ray vision cannot see it. But how do we know it exists? Because it exerts gravity. What is it made of? We don't know. There are experiments going on all over the world to elucidate the nature of this dark matter that pervades the universe. So let's return to the fate of the expanding universe in the last few minutes. Since there isn't enough matter in the universe to make it contract, our universe will expand forever and ever, just as a stone thrown up with sufficient velocity will eventually escape to infinity. But please remember, the stone may escape to infinity, but even as it escapes to infinity, it has to slow down because the Earth continues to pull it down because the gravity of the Earth vanishes only at infinity. Therefore, we would expect the universe, which is going to expand forever, to also slow down like a stone. So it came as a great shock a few years ago when astronomers discovered that the universe is not only not slowing down, but it is accelerating. And for this, last year, around the time this meeting was taking place here, the Nobel Prize was awarded to 3 astronomers for this astonishing discovery. Now, what does this result mean? The universe can accelerate only if something is pushing it, which means there has to be repulsive gravity. Not only there has to be repulsive gravity, but this repulsive gravity must exceed the attractive gravity due to the Earth. So for the situation on the right to obtain, the blue arrow, the repulsion, which is pushing it away from gravity, must be greater in strength than the attraction which is pulling it to the surface of the Earth. Now, I already said that it cannot be any form of matter that pushes the universe, because matter of any form, known and unknown, seen or unseen, can only produce attractive gravity. So what else is there in the universe besides matter? There is nothing. There is empty space. There is vacuum. So as Sherlock Holmes would have said, when you have ruled out all other alternatives, the remaining alternative, however improbable it may be, has to be taken as the truth. Therefore you ask, can vacuum or empty space or nothingness really be pushing the universe? The answer is it can. Now vacuum or empty space has energy, according to physics. Now, this energy is very similar like energy that we are familiar with. The energy is positive. But unlike matter, if I push a cycle pump, it gets harder and harder because the gas exerts pressure on me. The gas has positive pressure. Physicists know that the pressure exerted by vacuum is negative. Now, you may say, what has this got to do with the price of fish? Well, in Newton's theory, only matter contributes to gravity. In Einstein's theory, and this is the essential difference between Einstein's theory and Newton's theory, in Einstein's theory, all forms of energy, not just matter, contribute to gravity. And since pressure is nothing but energy, pressure also contributes to gravity. Therefore, something with negative pressure will contribute to repulsive gravity, just as something with positive pressure contributes to attractive gravity. Now, this is all very well, but the question is, can the cosmic repulsion be due to emptiness, vacuum, be significant? The answer is yes, indeed. Recently, astronomers discovered that the cosmic repulsion due to empty space is 3 times stronger than the attraction due to gravity due to matter in the universe. How did they come to this conclusion? Let us ask how much energy there is in the universe. Well, we know matter is associated with energy, as somebody said yesterday. Remember, E equal to mc squared. So you would think that if you want to know how much energy there is in the universe, take the mass of the whole universe, multiply by c squared, you get the energy. But when they measured this, they found that the actual energy in the universe is 4 times more than matter in the universe can possibly produce. Now, what else is there besides matter in the universe? There is empty space and vacuum. Therefore, empty space or vacuum is not only contributing to the energy, but it is contributing 75% of the energy. And since 75% of the energy produces repulsive gravity, it is not surprising that the universe is accelerating. But what is the nature of this energy associated with empty space? We simply do not know. So what do? You call it dark energy, like we called it dark matter because we didn't know what this matter was. So here is the energy budget of the universe. Only 4% of the energy of the universe comes from that yellow piece of the pie, which is the matter that you and I are familiar with. 23% of the energy of the universe comes from mysterious dark matter. We have no clue what it is. But more significantly, 73% of the energy of the universe is coming from nothing or vacuum. Now, please remember, empty space produces 73% of the energy of the universe. This energy produces negative pressure and therefore produces repulsive gravity. And even I know that 73% is more than 23%, 27%, and therefore the cosmic repulsion wins hands down over gravitational attraction due to matter. And that is why the universe is not only expanding, but accelerating. So before I conclude, I must say with all modesty that although we made unprecedented progress in 20th century in understanding matter and radiation, we seem to understand only 4% of the universe. The remaining 90% of the universe, we have no clue. So the nature of the dark matter that pervades the universe and the nature of the dark energy that pervades the universe are the greatest questions at the dawn of the 3rd millennium. But can I say something at least with confidence? Yes, even though we do not understand dark matter, we do not understand dark energy, this statement can be taken as a very solid statement that dark energy will produce cosmical repulsion, and since 73% is more than 27%, that the universe will not only expand, but it will continue to accelerate and become truly infinite. So our universe will expand and expand and expand, and eventually become unbounded, and it will become infinite. And hundreds of billions of years from now, long after life has ceased to exist in this universe, if an astronomer were to come back, he will find that due to the recession of the galaxies, the sky will get dimmer and dimmer and dimmer. And therefore, I should perhaps end by quoting Milton from Paradise Lost. Perhaps to move his laughter at their quaint opinions wide, hereafter, when they come to model heaven and calculate the stars, how they will wield the mighty frame, how build, unbuild, contrive to save their appearance. Thank you for your kind attention.